Welcome to this explainer, where we're venturing out into the busy Beaver frontier. We are talking about a mathematical mystery today that honestly starts off feeling like a simple child's game, but rapidly scales up to literally break the foundational rules of mathematics itself. It's not just a quirky math puzzle. It is a concept that directly challenges the ultimate limits of computers, logic, and human knowledge. Let's get right into it. So, imagine you're faced with this relatable little challenge. If you had a blank piece of paper and a ticking clock giving you just 15 seconds, how would you write down the absolute largest number you could possibly think of? Would you just frantically scribble down nines as fast as your hand can physically move?
I mean, intuitively, you might try writing a giant string of nines, or maybe building massive, towering stacks of exponents. It makes total sense, right? But to truly win the ultimate numbers game, relying on your handwriting speed to stack digits just isn't going to cut it. We need a totally different, special kind of conceptual program to do the heavy lifting for us.
Which brings us to our ultimate player for this game, the Turing machine. You likely already know the drill here. It's a theoretical machine working on an infinite, single strip of tape, interacting with just two symbols, usually a 0 and a 1. It simply follows strict, hard-coded rules to reassemble, write a new one, move one step left or right, or finally, to halt. It's the absolute foundational bedrock of computing, yet, amazingly, it's the very key to breaking math and transforming extreme simplicity into unimaginably massive numbers.
If we look at a two-state Turing machine, it operates on an incredibly simple closed loop of logic. It just relies on basic instructions telling it exactly what to do when it encounters a 0 or a 1, dictating every single move along its tape. There is literally no hidden complexity here, just pure, straightforward cause and effect.
Once you set it in motion, the machine progresses, step by step, along its blank tape. It acts almost like a little mechanical organism, flipping zeros to ones, shifting back and forth methodically, until it fulfills its instructions and finally hits that halt state, powering down for good.
Now, back in 1962, a mathematician named Tibor Rado turned this into a fascinating challenge. He called it the Busy Beaver game, and the goal is incredibly specific. You want to find an end-state Turing machine that runs for the absolute maximum number of steps on a blank tape before finally halting. So the machines that hold the record for running the longest, doing the most work before finally stopping, are crowned the Busy Beavers.
The known values start out completely deceptively small. A one-state machine runs for 1 step, and 2 states max out at 6. For 3 states, it's a very manageable 21. But by just the 6-state mark, the maximum number of steps explodes into this incomprehensible monstrosity. We're talking over 7.4 times 10 to the power of 36,534. It is a level of growth that just completely defies human intuition.
To truly grasp the sheer absurd scale of this growth, consider an 18-state Turing machine. The 18-state Busy Beaver completely dwarfs legendary mathematical titans. It produces numbers vastly, imaginably larger than Graham's number, or even the incredibly fast-growing Ackermann function. We are generating integers so massive that they make the total number of atoms in the observable universe look like a microscopic rounding error.
And the wild part is, this isn't just a machine outputting random, meaningless noise. The current 5-state champion behaves with incredible complexity. It actually performs intricate arithmetic loops, calculating patterns that fold back on themselves, taking over 47 million steps to finally halt. It's doing genuine, highly complex mathematical computation using nothing but a few basic rules.
So here's the crucial takeaway. This growth isn't just exceptionally fast, it is literally uncomputable. In computer science, this is a massive deal. It means there is no general computer program you could ever write that calculates the Busy Beaver numbers. Because if you could somehow predict an upper bound for this function, you would instantly solve the universally recognized, mathematically impossible halting problem. The proven fact that no computer can tell you in advance if a random program will run forever or eventually stop.
And this explosive growth builds a profound cosmic mystery. When mathematicians try to pin down the Busy Beaver function mathematically, it literally forces us to crash right into the philosophical limits of logic. By just exploring how fast these tiny theoretical machines can run, we end up reproving Gödel's incompleteness theorem. It's that deeply unsettling reality that there are true statements in mathematics that can never, ever be formally proven.
Because the function grows so violently and completely outpaces any computable system, the first 1,000 Busy Beaver numbers act like a literal cosmic cheat code. They actually encode the answers to the most profound mathematical truths we have. If we just knew the exact value for the 27-state busy beaver, we could definitively solve the famous Goldbach conjecture. If we knew the 744-state winner, it would effortlessly solve the Riemann hypothesis. It's absolutely mind-blowing.
But hold on, before we get too excited about solving all the deepest secrets of the universe with an ultimate math cheat code, we have to face a massive, insurmountable wall. There is a definitive, hard boundary to human certainty, and that absolute boundary is the number 748.
See, researchers proved that there is a specific 748-state machine that halts if and only if our standard foundational rules of math, the framework we call ZFC set theory, are fundamentally flawed. If our underlying math actually works and is perfectly consistent, this machine will just run forever. And because of that exact paradox, we can never actually mathematically prove the value of the 748th busy beaver. It is strictly unknowable within our current system of logic. We are blocked.
Okay, as a fun, much-needed palate cleanser to hitting that heavy philosophical wall of unprovability, mathematicians also define something called lazy beavers. Instead of looking for the maximum running time, they look for the least amount of time a machine cannot run for. And the really great news here, this function actually is completely computable. It gives us a bit of grounded, reassuringly solvable math in a total sea of infinity.
But as we stare back out into this vast computational horizon, we are left with some profound mysteries. We still don't even know if there is one true, essentially unique ultimate champion machine for these higher states, or if multiple, completely different designs can tie for the record. It really leaves us to wonder if a simple theoretical machine with just a handful of basic rules can entirely outpace human logic. What other profound truths are hiding out there, locked away in systems far too unimaginably complex for humanity to ever compute?